Hello everyone, welcome to this webinar on including variants of randomised trials in meta-analysis. This is part of online training for statistical editors and statisticians supporting Cochrane groups. My name is Jo McKenzie. I'm one of the co-conveners of the Cochrane Statistical Methods group, and I'm based at the Methods and Evidence Synthesis Unit at Monash University in Australia. And before I begin, I'd like to acknowledge the many methodologists and statisticians in Cochrane who have contributed materials to this presentation over time. Okay, so this is the session plan. I'm going to recap the inverse variance meta-analysis method, and then I'm going to talk through variants of randomised trials. I'm going to focus on the trials in red, so multiple intervention groups, crossover trials, cluster trials, in particular parallel group cluster trials. I will mention cluster crossover and step-wedge trials, and also multiple body parts, individually randomised trials with clustering, and factorial trials. The content in this webinar is based on Chapter 23 of the Cochrane Handbook, including variants on randomised trials. So if you need more information, then you can seek that there in the first instance. So to begin, I just want to recap the inverse variance meta-analysis method. It's a very common meta-analysis method, and it's implemented in RevMan. It's called the generic inverse variance method in RevMan. And under a fixed effect model, what this method does is it weights each study by the inverse variance of the effect estimate. So what this means is that studies where we can more precisely estimate the intervention effect will receive more weight in the meta-analysis than studies where we can less precisely estimate the intervention effect. Under a random effects model, there's a slight adaptation to the weights that's made that incorporates the estimate of the between study variance. The only data that's required to use this method is an estimate of the intervention effect and its standard error. And because of this, it creates a high degree of flexibility and allows us to incorporate these other study designs in our meta-analysis. So when undertaking a meta-analysis, we aim to give appropriate weight to individuals and trials. And if we're not careful, we can end up giving too much weight or too little weight to the individuals or trials. And this often occurs by making a unit of analysis error. So what I'm going to do in this webinar is really talk through some of these unit of analysis errors that occur. And I'm also going to touch on issues of bias that can arise in different variants of randomised trials. When I'm talking about variants of randomised trials, I'm really thinking that our standard trial design is a parallel group individually randomised trial that would have two groups. So let's begin just with this extreme example of a unit of analysis error. This is from a review that was published in JAMA, which was looking at inhaled anticholinergics and risk of major adverse cardiovascular events in patients with chronic obstructive pulmonary disease. And here we can see the meta-analysis that was presented in this publication. What I've highlighted here is this Brasco trial. And if you go and look at the underlying publication, primary publication of this trial, what this trial actually reports is the combined results from two trials. So going back to our meta-analysis, as it turns out, this Donahue trial is actually already incorporated into the results of this Brasco trial. So effectively, the participants in this Donahue trial are contributing twice in this meta-analysis, and obviously that's inappropriate. So this is an example of a unit of analysis level, a kind of gross level unit of analysis error. So I'm now going to move on to thinking about randomised trials that have more than two groups. So almost all our meta-analyses address pairwise comparisons of whether intervention A, what's the effect of intervention A versus B. So what do we do when we're faced with a trial with more than two intervention groups? Well, the first step is really to determine which intervention groups are relevant to the systematic review. So let's just take an example here. We've got a trial which has got three groups: nicotine gum, behavioural therapy, and placebo gum. If our systematic review only aims to address a simple question of whether nicotine gum versus placebo gum is effective, then really the only two groups that we care about from this trial are the nicotine gum and the placebo gum group. So this is a relatively simple situation to deal with. In the second example here, it might be the case that we actually have a systematic review that aims to address more than 2 questions. So it might be that we're interested in the question of whether nicotine gum versus placebo gum is effective and whether nicotine gum versus behavioural therapy is effective. So in this case, we've got these 2 comparisons and they're separate comparisons, and we can include the data from all the groups. So what we can include in the first comparison, we're going to include the data just from nicotine gum versus placebo. And in the second comparison, we would include the nicotine gum versus the behavioural therapy data. So again, this is an easy situation to deal with. The next situation is we need to determine how the trial will be included in the meta-analysis if more than 2 groups are relevant for a particular meta-analysis. So to investigate that further, let's look at a particular example. So here we've got an example where the review authors were interested in examining whether antibiotics are effective in inhibiting preterm labour. And this is the Oracle trial. It's a 4-arm trial, so we've got 4 groups. It's the largest and best trial in this particular group. And what we have here is we've got 2 antibiotics, and we have those 2 antibiotics in combination, and a group where neither receive any antibiotics at all. And the authors decided that all 3 antibiotic arms were comparable because their question was a very kind of broad question of whether antibiotics inhibit preterm labour. They weren't specifically asking the question of which particular antibiotic might be most effective. So let's have a look here. Here's a meta-analysis of this, and you can see that one option would be just to include the Oracle trial 3 times within this comparison. So this comparison is this broad comparison looking at the effects of antibiotics. So what we can see here is we've got the number of events out of the total number of participants for the group that's receiving antibiotics. And over here, we've got the control group. And what you can see is it looks like here that control group, if we include it like this, we're including the same participants 3 times. So that those participants are contributing 3 times in that control group the weight that they should. So how do we deal with this particular situation? Because that seems quite unreasonable. That trial, because of that, is receiving too much weight in this meta-analysis. You can see that that's up around over 66% of the weight this trial is receiving. Well, one very simple option is that we can actually just reduce the sample size in the control group. So we can just, in this case, divide it by 3 so that when we sum up across the number of events in the control group and the total number of participants, we get back to what the total number of participants were in the original control group. And that brings the weight down appropriately so that this trial is receiving in the meta-analysis. So that's one simple option. Another option is that we could just combine the events and the participants across the 3 antibiotic groups, and as is done here. So if I go back a slide, I can just sum across those events and sum across those participants and include this trial once in the comparison, as one comparison, the meta-analysis. And you can see here that we've got 96 events and 4,685 participants in our control group as it was originally. So now we've just included this trial once, and so that's another option. And what you can see here is that the weight for this trial is around about 50%. If it's the case, for example, that what the review authors were interested in was looking at particular types of antibiotics, so here we've got beta-lactam antibiotics, macrolide antibiotics, and macrolide and beta-lactam antibiotics, then the Oracle trial would contribute separately to each of these comparisons. And if they weren't being combined across, so there's no pooled total across these subgroups, then there is no issue again, because they're the trial is only contributing once to a particular comparison. So we need to be careful not to double count any group in a meta-analysis, because that will lead to a unit of analysis error. Approaches to overcoming that unit of analysis error in this particular situation is that we can combine groups to create a single pairwise comparison, and that's our recommended approach here. We could select one pair of interventions and exclude the others. This is not generally recommended because we're throwing away information if we do that. We can split the shared group into 2 or more groups with smaller sample sizes and include 2 or more reasonably independent comparisons. So that was the first example that I showed. We don't completely do away with the unit of analysis issue there because those comparisons, we're using the same control group, and so there's some correlation in the effect estimates there that's not accounted for in the analysis, but this is probably likely to have a trivial effect in for most meta-analyses. We can include 2 or more correlated comparisons and account for that correlation, or we could undertake a network meta-analysis. So really the simplest option, if it's possible, is this first option of combining groups to create a single pairwise comparison. Okay, I'm going to move on now to talk about crossover trials. So here's a depiction of the trial design that you're probably most familiar with. This is just a parallel group individually randomized trial. What we have here is at randomization, participants are randomized to receive the intervention or randomized to receive a control. And then at a certain point, we follow up their outcomes. Here's an example of a crossover trial and shows how it differs to a parallel group trial. In the crossover trial, we also randomize participants to an intervention and to a control group and measure an outcome. But in fact, those participants then cross over to receive the alternative intervention. So here we've randomized participants to receive the intervention followed by the control. And here these participants will receive the control group followed by the intervention. So for a crossover trial, we're essentially randomizing people to sequences of intervention. So here, intervention control or control and intervention. And these are given in different periods. So at the end of the first period here, we measure their outcome. And then again, once they've gone through to receive the next intervention or control, we again measure their outcome. So just looking at an example here, this is the effects of dihydrocodone on chemosensitivity and exercise tolerance in patients with chronic heart failure. And just looking at this particular example here, we've got the participants they're either randomized to receive dihydrocodone followed by placebo or placebo followed by dihydrocodone. And what is measured in this particular trial is breathlessness at the end of each period of receipt of that treatment. So why do people do crossover trials? Well, all individuals get both treatments. So in some ways they can determine what the best treatment is for the individual participant. The treatments, importantly, are compared with each individual rather than at a group level. So it can be a much more efficient design if there's less variation within an individual than across individuals. And what that means is that we need fewer individuals to get the same precision as we would in a parallel group trial. So that's a good benefit. What are the problems with crossover trials? Well, it could be the case that dropout risk is higher than in parallel trials, and this is due to the fact that participants are in the trials longer because they're receiving both intervention groups. It's not a suitable design where you've got an outcome such as death or pregnancy or some cure, because if that occurs at the end of the first period, then you lose the participant for the second period. A particular issue that arises in crossover trials is something known as period effects, where we have these systematic differences in responses across the periods that are not due to the treatments. So it could be that if you've got degenerative disease like dementia, there are kind of changes in the participant over time, or it could be that there are changes in background healthcare. Now, these period effects can be quite easily overcome by the design of the trial or the analysis. And then the other kind of, I guess, the major concern really is carryover effects, or what they're sometimes called as treatment by period interactions. And this is where the effects of the treatment that are given in one period persist into the subsequent period. And so by doing so, they can interfere with the effects of different subsequent intervention. So this can occur, for example, where you've got long-lasting drugs with a long half-life that are still in someone's system when you measure their effects and their outcomes in the second period. Or it could be that the effects of the intervention persist. And I guess an extreme example of that is where you might have, for example, in a trial, if you might have some type of cure, that's an extreme example of carryover. So really carryover is about the observed difference in treatments is dependent on the order in which they're received. And it's something that we really want to avoid. So some solutions to some of these problems are, we can really, it's only sensible to undertake crossover trials for chronic stable conditions that can be temporarily relieved. So these are often trials that are done in asthma, for example. We want to ensure that there's a reasonable washout period between treatments so that the drug can dissipate from someone's system. And to get around the issue of potential period effects, we can use balanced designs where we randomise an equal number of people to the sequence AB, for example, and BA. And we can also limit the potential for period effects to bias the intervention effect by adjusting for period effects in the analysis. So there's some of the solutions to some of the problems with this design. And this just is a depiction really of carryover. So looking at this example here, there's no carryover effect. So a person begins the trial, they have a baseline level for the particular outcome. They receive treatment, there's some response to that treatment. If we have a long enough washout period, then they kind of return to that state that they were at baseline. And then we can then measure their outcome again at period 2. But what you can see here in the second example is where there is a potential carryover effect, where they receive the intervention, they have some response to that, the treatment A in the first period, and then they have the washout, but the washout might not be long enough, and they don't return to their original state. And this then can influence the observation that's measured in the second period. Okay, so analysing a crossover trial, we can undertake a simple paired analysis if we can assume that there's no carryover effects. So this is just simply calculating the difference between the outcomes on the 2 treatments for each individual. We can then average these differences, and this provides us an estimate of the intervention effect. And we can just do a standard paired t-test. It's a little bit more tricky for binary outcomes. We can use the McNamara test, the Mantel-Heinzel test might be used, or the Becker and Balagatis method. And this is the recommended method, which takes account of the correlation in the observations within individuals. So in terms of now moving to a systematic review level, we should include crossover trials in principle. We shouldn't just exclude crossover trials because they are crossover trials. We need to consider, of course, if the crossover design is appropriate for the particular question. So it's obviously not appropriate where we can have permanent cures or where we've got unstable conditions. But if it is an appropriate design, then it's perfectly reasonable to include it in our systematic review and our meta-analyses. There might be some differences that we might want to investigate. For example, some crossover trials might tend to have shorter outcome follow-up than other parallel group trials. But this is a kind of external issue that we can investigate. We do need to consider the risk of bias of crossover trials, and there is a specific risk of bias tool that's been developed for that purpose, which you can find at the riskofbias.info website. I just want to highlight some particular risk of bias issues that are specific to crossover trials. So here are the bias domains. These are the standard bias domains 1 to 5 that we find for a parallel group randomised trial. There is a specific domain for crossover trials, And what this is really about is assessing the risk of bias arising from period effects and carryover effects. So looking at period effects, if it's the case, for example, that we've got an equal proportion of participants randomised to each intervention sequence, so the AB and the BA, then any period effects will just cancel out of the analysis. It could be that there is an unequal proportion of participants randomised to those different sequences, but if the analytical method that's used actually adjusts for that period effect, then this will remove the potential for bias, or at least minimise it. And also within this domain, what is assessed is the risk of carryover. Carryover effects should not affect outcomes measured in the second period, ideally. So we can have a long washout period between periods to avoid this, but it's not necessarily essential. The important consideration is whether sufficient time passes before the outcome measurement in the second period, such that any of the carryover effects have disappeared. So this domain, looking at the particular trial, you need to make an assessment as to whether that has been the case. Another particular issue under bias and selection of the reported result that occurs for crossover trials is when only results from the first period are reported, and the decision to report only the first period results is based on a test for carryover. In that case, just using data from only the first period will be biased. And so an assessment needs to also be made about that. So coming back again, so if we've got carryover and period effects, then what we can do potentially is just use the first period data and treat the crossover trial as a parallel group trial. If it's the case that we are worried about period effects and this hasn't been adjusted for, if the results are available by a particular sequence, then you can actually adjust for those period effects in a reanalysis. So appropriate crossover trials we can include in the meta-analysis with other studies. One of the major issues that kind of makes that more difficult is that many crossover trials haven't actually appropriately analysed the data. And the data is often reported as if the trial were a parallel group trial. And so the investigators of the trial haven't kind of appropriately incorporated the correlation that occurs between individuals with the data collected in multiple periods. So let's look at some of the data that might be reported. Ideally, this is the data that you would like to see reported. So obviously the number of participants, the mean difference, and the standard deviation of the differences. So this means I'm talking about here the difference between the within each individual between the observation in the first period and the second period, or under treatment A and treatment B. It might also be the case that, of course, there are other statistics that we would see. So we would see the standard error of the mean difference, confidence interval for the mean difference, the paired t statistic, and the p-value from the paired t-test. And so this is ideally what we would like to see. But what we often will see looking at these trials is basically the summary statistics are reported separately by the experimental and the control group. So we have the sample size, the mean, the experimental group, and the standard deviation of observations while the participants were on the experimental group, and those same statistics reported for the control group. It might be that, for example, we also have the standard error of the means reported. So what do we do in this circumstance? Well, we could seek the results from a paired analysis from the trial authors or the raw data so that we could reanalyze. If a paired analysis is not readily available, then we could ignore the pairing and treat the trial as a parallel group trial, which is equivalent to really assuming that the correlation between the pairs is zero. And this will lead to a unit of analysis error in that the trial will receive too little weight in the meta-analysis. Some people kind of consider this not such a sin as a trial receiving too much weight, but it could mask important heterogeneity. We could include data from only the first period, that, I guess, has the disadvantage that we're throwing away important information. And it's also possible, again, that the available data from the first period constitute this biased subset of all first period data. Or the third option, and I guess this is the option that we would encourage, is really to attempt an appropriate reanalysis of the data through imputation of missing standard deviations and correlations. So let's look a little bit more closely at that. So our effect estimate, we can just calculate is the mean difference or the difference in means equivalently. So this is just the mean in the experimental group minus the mean in the control group. And the standard error of the mean difference is calculated as the standard deviation of the differences divided by the square root of n, where n is the number of participants in the trial. Now, it might be that we have standard deviations of differences from the other trials, and we could just borrow that information from another trial within the meta-analysis. Or it could be that we could assume a correlation between the observations of the participants, and we could calculate standard deviation of the differences using this particular formula here. I should go back and explain that formula. This is the standard deviation of the experimental group, the standard deviation of the control group, and this is the correlation and the observations. So where would we get this correlation from? Well, we could get it from another study. So if we've got other studies in the meta-analysis that, for example, report the standard deviation of the differences and the standard deviation in the experimental and control groups, then we can use that information for another study to back calculate what the correlation is, and we can then use that correlation to calculate the standard deviation of the differences for the particular study in question. We could use this, we might have knowledge, for example, of what these correlations might be from other sources outside of the meta-analysis, or we can use some reasoned argument. It's likely that the correlation is going to be greater than 0, otherwise there wouldn't be a benefit in doing a crossover trial compared to a parallel group trial in the first instance. And we could, for example, make an assumption that the correlation might be 0.2, 0.5 or 0.8, and we could investigate what impact this would have in terms of sensitivity analyses. In fact, any time we are kind of imputing these parameters, it's really important that we undertake sensitivity analyses to see whether our meta-analysis results are robust to those underlying assumptions that we make regarding our imputations. So just having a quick look at an example, here we've got opioids for breathlessness, and we're using a standardized mean difference here. This meta-analysis here has got a number of crossover trials, and in those crossover trials, there's no adjustment for correlation. But when we account for the crossover design and account for that correlation, you can see here these trials that have confidence intervals marked in red are the crossover trials. And what you can see is that for each of these, it looks like we're able to estimate the intervention effect much more precisely when we're accounting for that correlation. So we're getting the benefit now of appropriately using a crossover design. And what you can see is that our pooled effect estimate here is very similar, but our confidence interval is tighter than when we don't account for the crossover design. Okay, so that's crossover trials. Now I'm going to move on to a different type of trial design known as a cluster trial. So coming back again to our parallel group trial, we randomise individuals. They're a unit of randomisation, and we also analyse at the individual level. But so, for example, we might answer the question of does self-monitoring of blood glucose improve HbA1c? We randomise participants to self-monitoring in usual practice, and then we measure their outcomes. In a cluster randomised trial, things are done a little bit differently. What we do here is we randomise participants, we randomise clusters to an intervention or control, but we measure at the level of the patients. So in this particular example here, which is answering the question of does audit and feedback improve GPs' adherence to recommended testing of HbA1c in their patients, we randomise GPs to audit and feedback, those GPs then will treat a number of patients, and we're measuring the outcome on the patients of whether they had received appropriate HbA1c testing. So our randomization unit here is different to the unit of analysis when we're analysing patient outcomes. This was a particular example just to highlight where I was involved in a trial looking at the effectiveness of hand sanitizers for reducing illness absences in primary school children. So what we did here was we randomized primary schools to either receive hand sanitizers or not, and then we looked at their infectious diseases after at the end of a school term. Why do we do cluster trials? Well, they're often done essentially because the intervention is targeted at the cluster. So education interventions for general practitioners, quality improvement strategies in hospital, water fluoridation to prevent dental caries. So these interventions are targeted at groups of people. We can also do it to reduce contamination between intervention groups. And in fact, this is an example of why we chose this particular option with the hand sanitizers in schools, because if it had been the case, for example, that we had put the sanitizers in primary schools and then randomized children within those schools to use or not use sanitizers, you could imagine what would happen, that in primary schools, children who'd been randomized to not using the hand sanitizers might have been quite keen to use the hand sanitizer machine. And so if that started to happen, then we would reduce our ability to determine if there was an effect of hand sanitizers or not. And so one way to kind of get around that is to randomize at a level of a cluster. And of course, there are logistical and political reasons. For example, if we were rolling out malaria treatments, it would be very difficult to potentially only apply those treatments to some individuals within a household. And so we generally would have households being the unit of randomization, or villages, communities, for example. So what's the problem with, or some of the issues with cluster trials? Well, the issue is that the responses of individuals within a cluster tend to be more similar than those of individuals in different clusters. And so there's this lack of independence in observations. And most of our statistical methods assume that we have this independence in observations. So this can lead to a unit of analysis error if we don't adjust for this clustering or this correlation that's occurring within the cluster. And we can end up getting artificially small p-values, increased false positive conclusions that the intervention is effective. So if we think about this at the extreme, if it's the case that individuals within each cluster are identical, then our effective sample size would be the number of clusters. But if individuals are no more similar in the same cluster, then our effective sample size is the number of individuals. So in practice, our effective sample size in a cluster trial is somewhere between these two limits. So if you were undertaking a trial, then I guess there are different options for what the analysis method might be. We can analyze at the level of the individual using statistical modeling methods that will account for this correlation, such as generalized estimating equations or random effects models. We could also analyze at the level of a cluster. And what you would do there is you could determine some summary statistic, for example, a mean or a rate for each of the clusters, and then analyze those summary statistics. Sometimes you might weight those summary statistics by the number of participants in the cluster. And essentially, if you use that approach, the clusters become kind of individual observations, and we are then accounting for the issue of the correlation. Or sometimes, in fact, what has kind of frequently happened is that analysis is undertaken on the individual, but there's been no accounting for correlation within clusters. And then this is the situation that the systematic reviewer has to make some type of adjustment to the variance of the estimate or the sample size. And we can do this using some quantity, which is known as the design effect. So here's the design effect. what we have is it's equal to this 1 plus m minus 1 times this quantity called the ICC. This m is the average cluster size. And this ICC represents something known as an intra-class or an intra-cluster correlation coefficient. And it's really equal to the proportion of the total variance that's attributable to the between cluster variation. And how do we interpret this design effect? Well, it's the number of times more participants of a cluster randomized trial should have compared to an individually randomized trial in order to obtain the same power to detect the same intervention effect. So more on this ICC metric. What does this really mean? Well, the ICC is somehow describing the similarity of responses within the same cluster. So if the ICC is 0, then it's saying that the participants within the same cluster are no more likely to have the similar responses compared with participants in other clusters. If the ICC is equal to 1, then participants' responses within the same cluster are identical. What happens with ICCs is they generally appear quite small compared with other correlations. So often they're less than, say, 0.05, but they can have a large impact on the standard error and the confidence intervals of the intervention effect, particularly if you've got large cluster sizes. So I can quickly just go back and show you. If you can see here, if this M is very large, then obviously this design effect can end up being quite large. So it's very much dependent on the cluster size. Even if the ICC is small, we can end up with large design effects. And I should say that ICCs generally appear quite small to other correlations. And when we were thinking about the correlations with the crossover trials, your correlations in that circumstance you would expect to be generally much larger than what you will see for these intracluster correlations. So where do we get information on what these ICCs are? Well, there are now lots of empirical studies that have really summarized the kind of sizes of these ICCs, and there's also general guidance. So I just list here some papers that have actually summarize the ICCs. This Corovar paper is actually looking at the circumstance where we've got longitudinal cluster trials and things are a little bit more complicated there. But the Health Services Research Unit, which I'll show on the next slide, also has put together a bit of a database that includes some examples of ICCs with different outcomes and different interventions. There's been some research to suggest that ICCs for patient outcomes are generally less than 0.05. By patient outcomes, I'm meaning kind of measurements on patients such as systolic or diastolic blood pressure. And ICCs for process of care outcomes are generally tend to be higher, so 0.05 to 0.3. And by process of care outcomes, I'm thinking about where the intervention is targeted, for example, at improving practitioners' adherence to, say, a clinical practice guideline, which might mean that they appropriately test for HbA1c or appropriately test for imaging under particular conditions. We know that larger clusters are associated with smaller ICCs, and the prevalence of the outcome is predictive of the magnitude of the ICC. So higher prevalence leads to higher ICCs. When imputing ICCs, again, sensitivity analysis should be undertaken to investigate the impact of the choice of the ICC. So similar to what I was talking about for crossover trials. So this is the front page of the University of Aberdeen, where they have spreadsheets that include ICCs that you can download. So you might be able to look at those. Here's an example of the spreadsheet. So you can look at the type of unit of allocation here as a general practice, the type of outcome, whether it's a process or a health-related outcome, binary or continuous, information on the prevalence, and then an estimate of what the ICC is. So in principle, now moving to the systematic review level, in principle, cluster randomized trials can be combined with other designs in the meta-analysis, again, using this inverse variance method. From trial publications that report results from analyses that correctly account for correlation, we can just extract the effect estimate and its standard error, and we can directly use that information in our meta-analysis. But if it's the case that in the trial they have analysed the individual level data, but they haven't accounted for autocorrelation, then we need to make some type of adjustment for that. And there's two ways we can go about doing that. We can adjust the standard error, or we can adjust the sample size and the number of events if we're using binary outcomes. The information that you would need to extract from the publications is the number of clusters randomised to each intervention group, or what the average size of each cluster is. Outcome data ignoring the cluster design, so the number or proportion of participants with events, or the means and standard deviations, and an estimate of the ICC. So we've already covered off where we might get that estimate from, either from other kind of sources or guidance, or it might be also that within the meta-analysis, there are other cluster trials and you could borrow the ICC from one of those cluster trials if that's reported. So let's have a look at a particular example here. This was a systematic review of controlled trials of interventions to promote smoke alarms. And the review included 3 trials randomised by cluster. Some of them were school cluster randomised trials, so they were randomising schools, and in others they were randomising medical practices. And this is just one trial, the Davis trial, which included 41 classes. So they randomised those classes. And what they had was an educational intervention, a safety class or a usual class. And then at the end of it, they measured smoke alarm ownership here. So from this information, this 2x2 table, we can calculate the odds ratio. So here we have an odds ratio of 1.28. And of course, for the meta-analysis, we would calculate the log of this, although this would all be done behind the scenes in RevMan. And we can also quite easily calculate the log, the standard error of the odds ratio using the usual formula. Now, coming back to this example, what we're going to do here is we're going to take the first option I talked about and adjust the sample size and the number of events by the design effect. So first of all, we need to calculate the design effect, and using that formula before, we've got 1 plus, we know there are a total of 857 participants in this trial. We've got 41 classes or 41 clusters minus 1 times the ICC of 0.02. So this gives us a design effect of 1.4. And we can use this to basically readjust our sample sizes here so that we're going to get the correct estimate of the standard error. So what we do is we divide the sample size and the number of events by the design effect. So if we just move to that here, we have 309 and was the original number of people who had ended up with a smoke alarm after attending the safety class. We can divide that by 1.4 and we get 221. So essentially we've now adjusted the number of events and the number of participants in the 2 groups. And when we do that, we can then just use our standard formula for calculating a standard error of the log odds ratio, which is 1 over each of the number of participants in each of these cells. And what we get is an adjusted standard error here. So our standard error is now 0.173. And comparing that to our unadjusted standard error, which was 0.147. So what we can see is that the adjusted standard error is accounting for this correlation, and it's slightly larger than the unadjusted standard error. And so what this would mean in terms of a meta-analysis is that this study would receive, in terms of a fixed effect model anyway, would receive slightly less weight. Coming back to this example, though, let's look at the second option, whereby we can just inflate the standard error by the design effect. So again, we just have calculated our design effect in the same way, which is 1.4. And all we need to do is to take the standard error, the unadjusted standard error, and multiply it by the square root of the design effect. So if we do that, we have 0.147 as our unadjusted standard error multiplied by the square root of the design effect, and we get the adjusted standard error of 0.173. So you can see that that is exactly the same as what we calculated when we used the other option of dividing the number of participants in each of the cells by the design effect. So let's just have a look at the meta-analysis then. These asterisks here indicate the cluster trials, and this first meta-analysis ignores clustering. And this second meta-analysis has accounted for clustering. So in this particular example here, our point estimates are pretty much the same. And also, as it turns out, for this particular example, our confidence intervals end up being quite similar. So in this particular example, adjusting for clustering is not really making a great deal of difference, but that's not to say that in every example that would be the case. So it is important to adjust for clustering when it hasn't been adjusted for in the primary studies. Okay, and let's just look again at some of the bias domains that are specific for cluster trials. So there is a specific risk of bias tool for cluster randomized trials. Again, you can find that at that risk of bias website that I showed earlier. Essentially, there are two domains, 1A and 1B, which kind of capture in fact, domain 1B captures issues of risk of bias that are particular to cluster randomized trials. One thing to note so domain 1 is equivalent to the bias arising from the randomization process. That's equivalent to what we have when we have to make that assessment in parallel group randomized trials. But something that often happens with cluster randomized trials is that because you have generally a small number of clusters, well, quite frequently there's a small number of clusters, and the clusters tend to be recruited all at once, the randomization is often done at one point in time, or it might be done in batches. So it's often the case that you will have less concern potentially about the randomization process in cluster randomized trials compared to individually randomized trials where participants are kind of sequentially allocated to intervention and control groups. This second domain here is specific to cluster randomized trials, and it's looking at bias arising from the timing of identification or recruitment of participants in the cluster randomized trial. So what commonly happens in cluster randomized trials is that, as I said, all the clusters are recruited, they're randomized to receive the intervention and control groups, and then once the trial's commenced, the participants are recruited. But by that point, of course, those who are delivering the intervention know that the cluster is receiving the intervention. And so because of that, there's the opportunity to selectively identify or recruit participants into the trial for the measurement of outcomes. So this is a particular issue that happens in cluster randomized trials and needs assessment in terms of assessing its potential to bias the intervention effect. I guess another point to make is that in a parallel group individually randomized trial, we have potentially data just missing on individuals, but in cluster trials, we can have whole clusters that drop out in addition to individuals that drop out within clusters. So there needs to be kind of consideration of data missing for both clusters and individuals within clusters. Okay, now I just want to briefly touch on cluster crossover trials, which bring together, in some ways, what I've talked about to some degree with crossover trials and cluster trials. So this is a cluster crossover trial is a variant of a parallel group cluster trial. And what we have here is an example where we've got 4 hospitals. In the first period, hospital 1 and 2 are receiving a particular intervention, and 3 and 4 are receiving another intervention. And in the second period, hospital 1 receives the intervention that hospital 3 and 4 had received in the first period, and also vice versa for hospital 3 and 4. So basically, it looks exactly like a crossover trial, except that what we're doing here is we're randomizing clusters to sequences of treatments. The design brings about the advantage of a crossover design, so we can remove between cluster differences and it means that we may require a smaller sample size than a parallel group trial. So that's a very beneficial aspect of this design. The analysis needs to allow for the correlation of participant observations within clusters, but this may depend on the separation of time. And so there are specific analysis methods that are needed for this particular design. And we can also need to consider specific risk of bias issues with this design, and so, which I'm not going to go into here. I just want to also touch on something known as a Stepped-wedge trial. This is a variant, again, of a parallel group cluster randomized trials. All clusters receive the intervention, but are randomly allocated a time when they receive the intervention. So it's like a one-way crossover cluster trial. And imbalance in the design with respect to time, so the analysis should allow for possible confounding by time. So what happens here, if I look here, all clusters or groups of clusters, they start in the controlled condition and they all ultimately end up receiving the treatment. So it's really a useful design for evaluating health policy changes, for example, particularly when those changes are just going to be rolled out anyway to each of the hospitals, for example. The analysis needs to allow for the correlation of participants' observations within clusters and over time. And also it needs to importantly allow for the fact that we've got more clusters receiving the intervention in the latter part of the trial than in the former part of the trial. So if there are these kind of secular changes, then they need to be adjusted for in the analysis. So that's a really important aspect of this design. Okay, individually randomized trials with clustering. So here's an example where we might be interested in a trial is examining the effect of cognitive behavioral therapy. Is it effective in improving symptoms of depression? Now, what happens here is we've got two intervention groups. We've got psychotherapy and no intervention. And we randomize participants to receive either psychotherapy or no intervention. But those participants may be seen by the same therapist. They might be randomized also to the therapist that they will see. And then we measure the outcomes again at the patient level. So what's happening here, of course, is that we have this clustering because we've got the same therapist essentially treating multiple participants. And so there could be correlation and observations that arise through that mechanism. So participants receive the intervention in groups. So we've got self-help groups or exercises classes, or it could be that we've got health professionals delivering the intervention to multiple participants, as I've just shown you with an example with psychologists, but it could be surgeons undertaking surgery on multiple participants or general practitioners. And this potentially leads to clustering in the same issues as was identified in cluster randomized trials. This is an issue that has been under-recognized in trials, but we can also, again, in the systematic review, deal with this by inflating the variance of the intervention effect using the design effect, using the similar methodology as we do for cluster randomized trials. And the impact of clustering, importantly, may vary by the arm. So it could be that we have CBT versus no intervention. We have some type of clustering occurring in the CBT arm because we've got obviously psychologists treating multiple participants in that CBT arm. But the participants who receive no intervention, there is going to be no clustering in that arm. Now, I want to just quickly touch on multiple body part trials. Obviously, people have multiple eyes, multiple teeth, and it could be the case that an intervention is rolled out and individuals may be allocated to interventions that are applied to multiple parts. So they might have cataract surgery on both eyes, for example, or some type of procedure on multiple teeth. If the analysis is by the individual units, clustering within the individual needs to be accounted for. So we're back in the situation where we've essentially got a cluster trial, where we've got multiple observations within this particular unit or person in this particular case. But it could be the case that what happens is that within person, we randomise one body part to receive treatment A and one body part to receive treatment B. So one eye gets treatment A and the other gets treatment B, and it could be the same with teeth as an example. In this case, we've essentially got a crossover trial, and so again, we need to account for that matching or pairing to get the benefit of reducing the between-person variation. So again, we can kind of use the methodology that we were thinking about, that we showed earlier for crossover trials. And the final trial I want to touch on is factorial trials. And I want to do this initially by looking at a particular example. This is an example that was, the authors were interested in looking at exercise therapy and manual therapy, or both, for osteoarthritis of the hip or knee. And so it's a 2x2 factorial design. And what it allows us to do essentially is to look at two, in this particular case, at two comparisons are compared simultaneously. So we really are running a trial in this case. It's two trials for the price of one. So here they were specifically interested in looking at exercise therapy versus no exercise therapy. So here we have, if we look along here, they're interested in looking at the how participants who received exercise therapy, irrespective of whether they received manual therapy, performed compared with those who received no exercise therapy. And similarly, they're interested in looking at whether manual therapy versus no manual therapy is effective for disability. So factorial trials address two or more simultaneous intervention comparisons using 4 or more intervention groups. And it's likely that only one comparison might be of relevance to the particular review. The results, ideally in a factorial trial, will report the results of the effect estimate for the comparison of, in this particular example, manual therapy versus no manual therapy, regardless of whether they received exercise therapy or not, and the effect estimate for the comparison of exercise therapy versus no exercise therapy, regardless of whether they received manual therapy or not. So factorial trials are used when there's not expected to be a substantive interaction, and that is that the effect of manual therapy in this particular example is not dependent on whether there was exercise therapy or not. There has been some empirical research done looking at whether interactions tend to occur in factorial trials, and in this particular study they found that only 2 of 44 factorial trials testing for an interaction had evidence that there actually was an interaction occurring. So it's suggesting that interactions are uncommon in practice. Because of this, this generally means that if I go back to the 2x2 table, that it will be reasonable if you're able to get this information to basically compare one of the comparison, irrespective of what the other other intervention they were receiving was in your meta-analysis. So then you can take full advantage of, in this case, the 112 participants randomized to exercise and the 112 participants randomized to no exercise. You do have an interaction, you have to kind of take a slightly different approach. Okay, so in summary, we need to be careful to give the appropriate weight to the included studies to avoid unit of analysis errors. We can often undertake an approximate analysis by making sensible assumptions about the parameters or using estimates from other studies. We should always report the assumptions that we make, and we should undertake sensitivity analyses to examine the robustness of meta-analysis method result to the chosen assumptions. So thank you for listening to this webinar.